This is Honors Math 3, and this is Objective 6 and Objective 7 together in Unit 7, the logarithm and exponential function unit. And in this lesson, we're going to find out about the change of base theorem for logarithms, compound interest, and half-lives. Okay, so first off, we're going to figure out what the change of base theorem is. We're going to discover it as we're going through and doing it. Okay, so got a couple problems here, and we're going to try to notice the pattern of what's going on. Okay, so log 24 base 3, and if we, it equals something, and so 3 to the what power is 24? Of course, 3 to the second is 9, so I would say that x is bigger than 2. On the other hand, 3 to the third is 27, so I would say that x is somewhere between 2 and 3, but it's probably a little bit closer to 3 because 3 to the third is 27. 27 is closer to 24 than 3 to the second is. And so that's kind of nice to keep track of, and so that you're thinking in logarithms a little bit here. Okay, so what do we do now? Well, much like when we were doing this in the first half of the unit, when we had no scientific calculator at our disposal, we're going to use the definitional logarithm. So we're going to do the base 3 to the exponent on the other side of the equal sign. So 3 to the x equals whatever's left there, which is 24. And so we've gotten it out of the log form and into the exponential form. Now, the first half of the unit, when we did something like this, we didn't need a calculator. If I had a base power of 3 on one side, I would have probably had a base power of 3 on the other side. And obviously 24 is not a power of 3. And so what we do, even though we have a scientific calculator available to us now, every scientific calculator really only knows, is only guaranteed to know 2 bases for logarithm. Some scientific calculators these days, they could actually plug in exactly what that looks like, log 24 base 3, but not every scientific calculator is like that, and so we need to understand how to enter log 24 base 3 into a scientific calculator, particularly if it doesn't have that button, because for our test, you might find yourself without that type of calculator. Okay, so here's how we do it. Where's the unknown? The unknown is up in the exponent, which means that we might need logarithm to help us finish solving this problem. And so what we're going to do is we are going to take the log of both sides, but we're going to take the log of both sides with a base that our calculator knows. Now, scientific calculators knows either base 10, common logarithms, or base e. But now that I've done the log, the exponent can be brought out in front because of log properties. So we have x log 3 equals log 24, and I can solve for x by dividing both sides by log 3. Now, we are trying to notice a pattern here so that we don't have to keep on showing a whole bunch of work to be able to know what to plug into a scientific calculator. So we're supposed to be noticing that log 24 base 3 became log 24 base 10 over log 3 base 10. Okay? And so we want to notice that. Okay, let's try one more of those. And it works very similarly. So equals x. And so we use the definitional logarithm. And so we've got 5 to the x power equals 1/12. And of course, we can't write 1/12 as a power of 5. And so we're going to take the log of both sides, base 10. And we're going to bring the x out in front using log properties. X log 5 equals log of 1/12. And we can solve for x by dividing both sides by log of 5 base 10. So log of 1/12 over log 5. Okay, and so log of 1/12 base 5, we would enter into a scientific calculator by doing log of 1/12 divided by log 5, and both of those are base 10. Okay, now by the way, the goal was for us to be entering them into a scientific calculator. And so right now you should be practicing that. So log 24 base 3, if you enter that into a scientific calculator, log 24 base 10 divided by log 3 base 10, and plug that into your scientific calculator, and round it to 3 decimal place accuracy. This would be 2.893 approximately. And if you remember, I said that log 24 base 3 was going to be between 2 and 3, a little bit closer to 3. Okay, so log 1/12 base 5, we enter it into a scientific calculator as log of 1/12 divided base 10 divided by log of 5 base 10. And so if we enter that into a scientific calculator, you need to be practicing this. You plug it in, make sure that you're able to do it. So negative 1.544 approximately. Okay, so now we're trying to notice the pattern, and so log 24 base 3 became log 24 base 10 divided by log 3 base 10. Log 1/12 base 5, log of 1/12 base 10 divided by log 5 base 10. And so the change of base theorem is if we have log x base y, we can write it as log of x base b over log of y same base. So as long as the base is the same, we can change the base to whatever we want. Now I was changing it to base 10 because every scientific calculator knows base 10. Now just for fun, the log 24 base 3, let's enter that as natural log of 24 over natural log of 3. And so if you plug that into your scientific calculator, I wonder if that is any different from what we got before. And what you find out, if you plug that into your scientific calculator, and you need to try it, 2.893 approximately. And that's exactly what we had before. And so that's what the change of base theorem, as long as the base for the top and the bottom is the same. In natural log, the base is e, and so that's why it still worked out. Every scientific calculator knows at least base 10 and base e. Okay, so we're trying some problems from the actual assignment as well, so help shorten the assignment and do some extra problems. We are solving, this is 7.6, number 12. And so as I look at problem number 12, I notice that the unknown is up in the exponent. Anytime the unknown is up in the exponent, there is potential for needing logarithms to help finish solve the problem. So what would we do first? Well, I would add 29 to both sides of the equation, and then we would get 2 times 5 to the x equals 1029, and then we would divide by 2 or multiply by 1/2, and so either way you do it, you get 5 to the x equals 1029 divided by 2. Now 2 does not go in evenly. Now you could just go ahead and tell me what the decimal value is. It turns out to be a 0.5. The key is make sure you don't round. If you round in the middle of the problem, you're just getting error in your answer. You don't round until the very end of the problem when you're actually plugging the numbers into the calculator. So make sure you don't round. I'm just going to leave it as a fraction, 1029 over 2. Now, 5 to the x equals 1029 over 2. Can I write 1029 over 2 as a power of 5? Of course not. So I need logs. So I'm going to take the log base 10. Actually, that's kind of a long way to do it. So instead of doing it that way, sorry, I got caught up a little bit here. We do want to get it into log form, but I'm not going to take the log of both sides because that's kind of a long way to do it. So what we are going to do is we're going to convert to log form. Now, first half of the unit, we were converting things from log form to exponential form, so going from exponential form to log form is probably a little bit weird, but just take your time. Now, what's the base? Well, the base number here is 5 because it has the exponent, so the base of the log is 5. Leave a little bit of space, equal sign, and then the exponent goes on the other side so that we could do the definitional logarithm and convert back. So notice base to the exponent, okay. And then right here is the 1029 over 2. Okay, so that's x. We've solved for x. Now, to get the decimal value, remember what that is equal to. And remember how to enter that into your scientific calculator. So that would be log of 1029 over 2, or you could do the decimal value divided by log of 5. And I'm doing those both as base 10. So anyway, if I plug that into my scientific calculator, I would get 3.879 to the nearest thousandth. And you guys need to be practicing that. Okay, 7.6, number 16, still solving. Where is my unknown? My unknown is up in the exponent, so I might need log here eventually to be able to finish solving the problem. And okay, so what would I do first to solve for x? I'm going to subtract 9. So we have 1/2 e to the x plus 1 equals 1957. Okay, and I'd divide by 1/2. Well, that's kind of weird. So let's multiply by 2 instead. And so we get e to the x plus 1 equals 2 times 1957, which is 3,914. Okay, can I write 3,914 as a power of e? Of course not. So log, what's my base? My base is e. Wait a minute. If my base is e, what type of log is it? It's natural log, isn't it? Now, if you start to recognize that it's going to be natural, you can just go ahead and go straight to natural log. On the other hand, it's not the end of the world to have log and then base e. It's just on the next step, make sure you convert it to natural log. Okay, so where's my exponent go? So the exponent goes on the other side of the equal sign, and then the 3914. So we're doing natural log of 3914, and that's equal to x plus 1. Of course, what's left to do? We do natural log of 3914, and then we subtract 1, and that's what x is. Now, decimal approximation. So grab your scientific calculator, do natural log of 3914, and then subtract 1. And if you do that, you get x is approximately 7.272. And you need to practice that. Make sure that you know how to use your scientific calculator. Okay, next thing on the title was compound interest. And there's two formulas here. And you need to know what all the different letters mean. And it's written out here. And if you need to stop the video to write out what all the different letters mean, then make sure you stop the video and write it out. The formula on the left is for a finite number of compoundings. So in other words, it's not an infinite number of compoundings per year, per annum. And the formula on the right is for an infinite number of compoundings per annum, or the keyword is continuous compounding. A for both formulas is the amount of money after t years. P is the principal which is the initial investment. R is the interest rate as a decimal. Make sure that you enter it as a decimal correctly, not as a percentage. T is time in years. N in the first formula, it's not in the second formula. N in the first formula is the number of compoundings per annum, in other words, per year. So for example, quarterly compounding, there's 4 quarters in a year, so N would be 4, something like that. E, formula on the right, is the actual number E, but don't use the approximation. Make sure that you're using the E to the X button on the calculator. Okay, so here's a sample problem. It has a part A and a part B. So if we're investing $5,000 at 6% interest, how long will it take for your investment to triple in value if its interest is compounded semi-annually? So one of the first things you really want to do is you want to figure out which formula you're using and where is that information. Well, the interest is compounded semi-annually. That's where it tells us. So is that infinite number of compoundings? No, semi-annually. There are 2 semi-annuals per year. So we're using the formula on the left. So A equals P times 1 plus R over N to the NT. Okay, so that told us that we're doing that formula, and it's 2 semi-annuals per year, so N equals 2. Okay, the $5,000, that's the initial investment. That's P, the principal. 6% interest, that's 0.06. How long will it take? Okay, so we're solving for time. Okay, so let's start plugging some things in here. So we've got principal is $5,000. And by the way, we're tripling it in value. Triple 3 times. 3 times 5,000. And we've got 1 plus R, 0.06, over N. N is the number of compoundings per annum, so 2. And it's to the power of 2t, because we're solving for time. Okay, it's all set up. What would we do first? Well, I'd probably go ahead and divide both sides by 5,000 first. And so if we do that after one step, I have 3, excuse me, on the left side equals 1 plus 0.03 to the 2t, which 1 plus 0.03 is 1.03. Can I write 3 on the left side as a power of 1.03? Probably not. My unknown is up in the exponent, so I probably need logs. Okay, so let's use logs. We were just doing this stuff on the last couple problems. My base is 1.03. Where's the equal sign? There's the equal sign. 2t goes on the other side so that I could do the definitional logarithm, 1.03 to the 2t power, and then the 3 would go right there. Okay, so the only thing left to do to solve for t is to divide by 2 or multiply by 1/2. So t is 1/2 log of 3 base 1.03. Now remember how to plug in the log 3 base 1.03 for a scientific calculator. I mean, this is the value, but we need to be able to plug it into a scientific calculator as well. So if we plug that in, log 3 divided by log 1.03 times 1/2, and we get approximately 18.584 what? What are the units? Well, it's t is time, and it's in years. Okay, and that's an important thing to pay attention to, because you guys are going to be investing for your retirement someday, and compound interest when you're investing for your future is definitely to your benefit. In general, it's the more compoundings, the better. Of course, a better interest rate is also better too. You know, your money's working for you there. It grew to $15,000 in a little less than 20 years. Okay, so same problem, but instead of the interest compounding semi-annually, this one, the interest is compounding continuously. Okay, so which formula are we using? By the way, the two formulas are going to be on the test. You don't have to have them memorized, but you have to know what all the letters mean, and you have to know which formula is which. So compounding continuously, is that the formula on the left? No, it's the formula on the right. So compounding continuously. So we are going to be doing the formula A equals P e to the RT. Okay, so now it's this formula, but we're still using the other information that we had before. So $5,000 initial investment, it's going to triple in value at 6% interest. Okay, so 5,000 invested, it's going to grow to 15,000, triple the value. E, the interest rate was 0.06, and we're solving for T. Okay, first thing that we would want to do is we divide by 5,000, divide by 5,000, and we get 3 equals e to the 0.06t. Can we write 3 as a power of e? No, so we need logs. Okay, so log, and it's base e, and you go, oh, it's actually natural log. So you could, as soon as you start recognizing that kind of stuff, you could just go immediately to natural log. Now, on the other hand, it might still be helpful to go ahead and write in the base, even though you're writing natural log. So e, there's the equal sign, the 0.06t goes on the other side of the equal sign, and that means you've got 3 right there. Okay, so solving for t, we're going to divide by 0.06. So t is natural log of 3 over 0.06. Okay, but we want the decimal value, so plug that into the scientific calculator and check, and you should be getting approximately 18.310 years. Now, it was all the same information except for the number of compoundings were different for the two problems. Which one had more compoundings? Well, continuous compounding has an infinite number of compoundings per annum. And so if the number of compoundings, if everything else is equal, if you have more compoundings, it's better for you. So it did triple in value a little bit faster. It's not a huge amount, but given enough time, it does make big differences. Okay, so when you're earning interest, you want more compoundings per annum. By the way, if you're ever borrowing money, you never ever want to borrow money that's compound interest. Never, ever, ever. You want simple interest. Okay, number 7.7. This is from worksheet 7.7, and it's problem number 18. How long for an initial investment to quadruple? Okay, quadruple. That's 4 times. If invested at 8.5%, okay, 0.085, compounded quarterly. Okay, so this is the finite number of compounding, so A equals P times 1 plus R over N to the NT. Okay, wait, it didn't tell us how much to invest. It just said we're going to quadruple. So you get to choose how much you're going to invest. I think it's good I just invest $100. Okay, it's going to quadruple in value, so that would be 4 times, so it's 400. 1 plus, there's my interest rate, 0.085 over number of compoundings, quarterly, 4 to the 4t. If we do the, well, actually, first step, I'd divide by 100 both sides. And so after one step, I've got 4. Look at that, I'm quadrupling, and I've got 4 on the other side after one step. 0.085 divided by 4 plus 1, okay, that is exactly 1.02125. Make sure that you don't round whatever's on the inside there. If you had to round, you'd just leave it as an expression, but I didn't have to round. Let's see, it looks like I need logs because my unknown is up in the exponent, so log, and my base is 1.02125, long base, and equal sign, and there's the 4t, and 4 goes right there. And the only thing left to do is to divide both sides by 4, or multiply by 1/4. So t is 1/4 log of 4 base 1.02125. Okay, now you need to remember how to plug in the log of 4 base 1.02125. And so log of 4 base 10 divided by log of 1.02125 base 10. Plug that in, multiply by 1/4 or divide by 4. And if you do that, you get approximately 16.482, and it's t, time, years. Look at that, we quadrupled our money. Why did it take less time? Well, the interest rate was better, 8.5%. That was better than the 6% that we had on the other one. Number 20, what initial investment is needed to attain a value of $500,000 if invested at 11% compounded monthly for 20 years? What initial investment? Isn't that P we're searching for? And the 500,000 is A, and 11% is 0.11, and compounded monthly, that's the number of compoundings, that would be monthly, so N is 12, and 20 years, that's time. Okay, so we're using the formula A equals P1 plus R over N to the NT. And we're solving for P, so 500,000 here equals P1 plus my interest rate 0.11 divided by 12 to the, okay, compounded monthly, so 12 times 20. Where's my unknown? It's not in the exponent. My unknown is not in the exponent. I'm not going to need logs. Now, if I try to do the 1 plus 0.11 divided by 12 and clean up the inside of the parentheses, it's just, I'd have to round. So leave it alone. Don't try to clean up the inside of the parentheses. Now, my exponent is 240. How do I solve for P? Don't we just divide by that mess? Yeah. So we're going to divide by 1 plus 0.11 over 12 to the 240 power. 1 plus 0.11 over 12 to the 240 power. Okay, so P, that's what P is equal to. P is equal to this. And you need to be able to plug it in the calculator, and it's a little bit messy, but you've got to be able to do that. And so if you plug that in, you will get 55,959.61. And why did I stop at 0.61? Well, because P is the initial investment, which is money, and money, we just round to the nearest penny. Okay, so that's compound interest. The other thing we had that we're talking about are half-lives. And half-life, that's the stuff that's happening in science, and there's all kinds of applications for it. And so now when you're doing the half-life, we need to make sure that we actually understand what's going on. So half-life is the amount of time it takes for half of a particular substance to change or disintegrate or go away, kind of thing. So the amount of time it takes for half of a particular substance to change or go away. So we need to do a sample problem, and let's just do from 7.6, we're going to do number 20. So the half-life of cesium-137, by the way, 137, that's just part of the name. We're not going to be plugging in 137 anywhere into the formula. So the half-life of cesium-137 is 30 years. So in 30 years, if you start with a certain amount, half of it's going to be gone in 30 years. Find the constant K. K is a constant. In the formula, A equals A sub 0 e to the negative KT. Now, when we're doing half-lives, like I say, you have to understand what the definition is, which is why I started with it. But they're always going to give you whatever formula you need to work with when you're doing the half-life stuff. And this is a very common formula, A equals A sub 0 e to the negative KT, but just use whatever formula that they say to use. Now, whatever formula they give you, having this A sub 0 thing, that's a very common thing to show up in the formula. What does that mean? So when they have that sub 0, it's the A, which amount, it's the amount at time 0. The amount at time 0. Oh, in other words, the initial amount. Which is kind of like what we were doing for the compound interest. The principal was the initial investment. It's just the money people didn't want to use A sub 0. And so, therefore, because they didn't want to use A sub 0, they used P for principal. And but it's just the same thing. You could put A sub 0 there, and it's still the compound interest formula, whether you do it with a P or A sub 0. Okay, so now the other thing that happens when we're doing these compound interest, or not compound interest, but the half-life problems, a lot of times it seems like they're just not giving you enough information, but they are. And so let's take a look at that problem again now. So the half-life is 30 years. Okay, so, and we're using this formula, the amount at time 0, in other words, the initial amount. Now, my recommendation is, and by the way, take a look, they didn't tell us how much we're starting with. So my recommendation for the amount to start with, particularly with half-life, is just start with 100 of whatever it is. It makes it a lot easier on yourself. So A sub 0 is 100. Well, the half-life is 30 years. So if I use the 30 years, how much will A be after 30 years? Well, half-life, this is how it works. So 30 years passes, half of it will be gone. So I'll be down to 50. And then I've got E, and I'm trying to solve for K, and T is time. Now I just did 30 years. Because I started with 100 and now I only have half of what I started with, so I have to plug in a 30 right there for T. And if you look, the only thing we don't know is K. So I'm going to divide by 100 to begin with, or multiply by 1 over 100. And I get 1/2 equals E to the negative 30K. And we look and we go, okay, well, the unknown is up in the exponent, and I'm not going to write 1/2 as a power of E, so we need logs. So, and the base is going to be E, so it's going to be natural log, but I'm going to go ahead and write E right now. So, other side, I've got negative 30K, so that I can use definitional logarithm E to the negative 30K equals 1/2. Okay, what's the only thing left? We divide by negative 30. So K is natural log of 1/2 over negative 30. Okay, and so we plug it in to the calculator, and it's approximately 0.023. Now, a lot of times when we're doing the constant in these half-life formulas, you do like 4 or 5 decimal place accuracy. So 0.0231. Number 7.6, problem number 24. 23, 24, 25, they're telling us to use this particular formula. Now remember I told you, use whatever formula that they're telling you to use. You don't get to use the formula that you want to use the formula that they're telling you. Okay, so A equals A sub 0 times 1/2 to the T over 5700. Okay, 38% of the material for a certain artifact is still present. What is the age of the artifact? So we don't know how much we started with, but I suggested use 100 to begin with. Okay, so if we start with 100, they're estimating that approximately 38% of what we started with is still there. So 38 is 38% of 100, isn't it? And this is part of the reason why I told you choose 100 to start with, because it's really easy to figure out how much you have after a certain amount of time. So 100 times 1/2 to the T over 5700. What would we do first? Well, we'd go ahead and divide by 100. And after one step, we would have 0.38 equals 1/2 to the T over 5700. My unknown is up in the exponent, and so I might need logs. So log, my base is 1/2, and equal sign, and T over 5700 is on the other side, and 0.38 right there. Okay, so the only thing left to do is to multiply both sides by 5700. So T is 5700 times the log of 0.38 base 1/2. Okay, now remember, this is what we started with, the change base theorem, so plug that into your calculator. So log of 0.38 base 10 divided by log of 1/2 base 10 times 5700. And so we get, if you plug that in, you should be getting approximately 7,956.793 years old. Kind of old. Okay. Now, logarithm is a wonderful tool. Don't use logarithm for every problem. Make sure you use logarithm where it's appropriate. If you use logarithm for every problem, you're going to be missing some problems. It's used when we need it. Okay, so still doing some more problems from the homework. Let's go ahead and try these. Everything that is new, we're done with everything that's new, but we're just still doing some sample problems. Okay, so solving. 3 times 2 to the negative x equals 273. Where's my unknown? It's up in the exponent. Might need logs. I'm going to divide by 3. And so after one step, I've got 2 to the negative x equals 91. Okay, can I write 91 as a power of 2? No, so log. Base is 2, negative x on the other side, 91 right here. And so x is going to be opposite of log 91 base 2. And you know how to plug that into your scientific calculator. So I do log 91 base 10 divided by log 2 base 10, and then make it negative. And so if we do that, and plug it into the scientific calculator, you get x is approximately negative 6.508. So practice that in your scientific calculator. Okay, problem number 6. Where is my unknown? Is it in the exponent? No, it's down in the base. If the unknown's not up in the exponent, we're not going to need logarithms. But let's see what we do. Looks like I would divide by 15 on both sides to begin with. And so we get x to the 5/3 equals, I don't know if that reduces or not. I mean, you can try to reduce. We do have scientific calculator. It actually does reduce. It reduces to 209 divided by 5. You know, I mean, you could do it as a decimal because it's not being rounded. What would I do to solve for x? Not logarithm. Well, x to the 5/3, we can raise both sides to the reciprocal power 3/5. And so now what do we do with the exponents here on the left side? I'm multiplying, so I get x to the 1st, which is x. And so it's 209 divided by 5 to the 3/5 or 0.6 power. Now, without scientific calculator, you know, that's all you can do because we're not going to be doing 5th root and then cubing it kind of stuff. But we need to understand how to plug that into a scientific calculator too. Now my suggestion, make sure you put parentheses around the fraction, or you do it as 0.6 when you raise it to that power. So anyway, if you do that, that's approximately 9.391. Make sure you practice plugging that in, because all these kind of things you're going to have to be able to show that you can plug them into the scientific calculator and be 3 decimal place accuracy. 7.7, problem number 10, solving. Okay, so looks like I would subtract 1,500 to begin with, and then we would have 3,500 equals 300 natural log of x, and we could divide by 300, divide by 300, and we get natural log of x equals 35/3. And what do we do now? Well, don't forget that the base is e, so we can use definition of logarithms. So e to the 35/3 is x. Okay, but we need to be able to do that on a scientific calculator as well. So e to the 35/3, if you plug that into the scientific calculator, you should be getting 116,618.904. 3 decimal place accuracy. Last one, solve for x in terms of y. So this is 7.7, it's problem number 14. So if we have a formula, we should be able to point at a letter, and you should be able to solve for whatever letter we point at this point. Okay, so we're solving for x, we're unlocking it from everything, and getting x equals, and there will be a y somewhere involved, and we need to clean it all up and all that kind of stuff. So, looking at this, I think I would subtract 10 first. And so we get y minus 10 equals log of 1 over x base 2. And we look and we go, oh, we could use definitional logarithm. So 2 to the exponent 2 to the y minus 10 equals 1 over x. Okay, now we're solving for x, not 1 over x. Of course, 1 over x is x to the negative 1. So I could raise both sides to the negative 1 power, because 1 over x to the negative 1 power would be x to the 1st. And we multiply the exponents over here, so we have 2 to the 10 minus y power. And that's what x is equal to. I mean, that's really about as clean as it gets.